Okay, so let's try again. The only I restarted the container, I restarted Docker, and I redeployed. I use this command here to redeploy the sandbox. That has reset everything to the starting state, which means that the contract has to be redeployed again. Then I run this command here, okay, and it deploy the contract to this address. It's here, this address here. And if I try again, then it gives an error. The issue I had before was that when it gives an error, it doesn't give you the deployed contract address. So if this command fails, I don't know how to find the address. But it is expected that you can't deploy the same contract twice. There's a replay protection. Anyway, we're here, and then okay, we can try to do this stuff. So what does it mean? We have a secret. I don't know. Okay, I think the secret is just random, and the secret hash is a hash. Well, we probably just hash the secret. Right, we need to export the secret and secret hash. Alright, so we do that later. Just a tutorial here. So for the moment, I'm simply gonna run these commands and see if we're able to do that. And afterwards, we're going to look at what this stuff means. Okay, so let's run this stuff. It should not cause any problem. Okay, Aztec send min private, then the argument, and then it shows the mint stuff, right? Possession mine, status mine, and then okay, seems to be okay. Then we can transfer this guy to Bob. So this is essentially the same thing as a ERC20, except that it's private. So that's way better transaction hash for this transfer. And then we asking the balance, and we have 500. Okay, so I did send 500 to Bob. Yeah, 500 tokens. What's next? Let's dig more into the sandbox. Okay, so what do we have? It's saying that layer 2 network is a fully programmable combined private and public ZK rollup. Uh, okay, so if you're not familiar with ZK rollups, the idea, at least for the public ZK rollup, it means that okay, so when you have a smart contract and the smart contract runs on Ethereum, the this is L1. Ethereum is a layer 1, meaning that the contract is the code, and the contract contains state, which is basically the values of all the variables of your contract. Typically for ERC20, the variables will be something like the outstanding supply, which address has that many tokens. Basically, who owns what. So the cool thing about Ethereum is that each contract can have as much space as you want, except that you have to pay for the space, of course, with your when you make a transaction. A contract itself can have basically the whole state of a coin, such as like the entire history of Bitcoin, for example. So the problem being that as you make transactions on L1 and you want to modify that state, the uh, every node has to execute the transaction, so same as Bitcoin, and everyone has to pay the fees. So it can become expensive. Like in Bitcoin, it's pretty expensive. So the idea of a layer two rollups is that people make these transactions from peer to peer, or at least outside of the Ethereum network. So it's not always peer to peer. It could be going through the platform of a particular side chain. It could be, for example, the exchange that is backing the particular L2. But the key point is that the transactions do not hit the Ethereum network. So in a sense, i- is out of band. And of course, the problem with that is that if you do that outside of Ethereum, there's no Ethereum does not know the main contract on Ethereum does not know what you have done, what people have done on the off band, out of band. So in order to capture that change, uh, the guys were running the sidechain, the website or the exchange on the out of band. They commit the end result of a series of transactions. So they don't need to commit the result of one transaction because then the result will be the same. You will have to pay a lot of fees because you are basically executing every update on the main chain, on the Ethereum chain. The main idea is that you collapse all many of these transactions into a bigger one, an aggregate, and then you apply the change into the Ethereum chain. But since there's no, if you just do that, there's no proof that these transactions actually were really existed. We You have to provide a proof that these what you are committing on the main chain actually reflects the changes that you have made on the L2. And the way to do that is to do the zero knowledge, because basically a zero knowledge proof is is one piece of information. So uh, it's a it's kind of like a series of action collapsed into one, but the proof is there to show that these actions were not faked. They really existed. All the data that were necessary to create that aggregate uh, were provided at some point to the zero to the prover. Right? So because many of these elements of the transactions are hashes, and if the proof is built properly, the proof cannot be built without knowing these hashes. Therefore, the prover cannot create a zero knowledge proof without actually knowing the actual data that the transaction contain. So that's the idea. But so far, the chains have been doing that based on transactions that were public. All the data that you are rolling up, all the data that you're merging into a zero knowledge proof were provided in clear. The exchange were uh, doing this roll up is getting this information from their customers, from the traders, and the information that they got from the traders were just regular Ethereum transactions that could have been done on the main chain, but happened to be done on the L2 to save on gas. So the structure of the framework, or structure of the environment to run L2 mimics the environment of L1. The L1 has also a contract, typically the contract that you want to replicate in L2, but it has now also a verifier that is specific to that contract, so that instead of submitting the transactions on L1, you can submit them on L2 and only verify the aggregate and the zero knowledge proof. So you're moving the contract from L1 to L2. So the issue with that, or not the issue that, but the challenge with that is that as you're moving from L1 to L2, the ZK proof that you have is specific to the particular contract that you're replicating on L2. And I think this new thing, this Aztec, will allow you to create zero knowledge proof for on probably, I don't know if it's 80, but for many of the smart contracts that that you could have built on L1. So which is a win situation for you because you just learn how to write a normal contract for L1. At least that's the premise behind Polygon. Polygon is a rollup where if any contract that you write in Solidity that you can run on, I don't know if it's any, but most contracts that you can run and can you write in Solidity and they can run on L1 on Ethereum can be turned into a contract that is run on the ZK EVM, on the zero knowledge EVM, on the Polygon. And therefore, you can translate most of your business, your application logic from running on Ethereum to running on their Polygon EVM. And therefore, at a much lower cost in gas. But this guy, I think the difference is that your contract, so your smart contract, can have data that is private, right? But the structure should be the same. So we have Aztec node, right? Aggregates all the backend services necessary for the building and publishing of rollups. So this is the stuff that earlier we defined as a web service or the website or the infrastructure that the ZK rollup dudes have built outside of the main chain. So that's that part. The private execution environment. Okay, normally residing with the end client, this decrypts and stores the client private state, executes simulation, and submits transaction to the ASIC node. All right, so here what we have is that since the smart contracts can have private data, the private data is going to be encrypted on the client, and the it stores the client private state. Oh, so that's interesting. It means that if you're responsible for storing your encrypted data, so it means that this data is never going to leave your node, or if it leaves your node, it's going to be sent as encrypted data to the other node, and probably the validity of that private state is going to be enforced by zero knowledge proof as well. Um, so they really have this notion of private state at the client, which is very interesting because, for example, in the case of Zcash, what you could say is that the memo that you associate with the transactions could be private state, and you're not putting that private state into the blockchain, which really makes sense because uh, most people, I mean, the memos should be really be sent peer to peer. The destination should be aware of the content of the message. At this point, every message, every output on Zcash has this memo field that takes about a half a K. It's really hard, it's pretty large. It takes half a K, and most of the messages do not really contain anything significant. The memo is an empty field, but it's encrypted and it looks like it was full of data, even though there's really nothing there. So I really like that. And then afterwards, so this PXE key point is that it's running on the client. And then we have Aztec.js. Okay, so that's the client library to the client logic if you want. Uh, so this guy is probably written in like Rust or some low-level language, but this is uh, the client library to that internal library. All right, so I think that okay, it says though that this is mocked at this point, so they haven't done this yet. Okay, it's fair enough. Still work to do, and okay, so Aztec.js is probably what they expect users or the developers, not the core team. The core team will work on the PXE and the Aztec node. So I think they expect people to use Aztec.js. Seems like their core, the main customers, the main customers. They're targeting users of JavaScript, and they must have a smart contract language as well, because this is the equivalent of Web3J. You have an API to create an account, makes sense. To deploy a contract, of course. These call view methods on contracts. So contracts have two kinds of methods. You have methods that mutate the state, and usually you pay gas for that because as you're mutating the state of the contract, this is data that has to be replicated. If you instead just want to see read the value of a variable, you can do that at no cost because if you're running a node, if you're running one of an Aztec node, this guy will be getting the data from the blockchain, and since it's already validating the blockchain, it has recalculated the state of every contract. So that's free because that's free in gas, but it's not free in compute resource at on your machine. Simulate the calling of contract functions. Okay, so that the contract functions are the guys that mutate. I think that the idea here is that this is a sandbox. The stuff is not fully operational. So at this point, when you're calling a contract function that mutates the state, it's not there's no blockchain yet to really apply this because the Aztec node is is currently under development. Okay, then send transaction to the network. That's the broadcasting of the state from the PXE, and then you have transaction settle. So when the stuff is mined, you need to know if it has been applied, and then you can have this is the stuff that Block Explorer would need: the chain ID, block number, blah blah. All right, what's in the sandbox? The sandbox contains an instance running NVIDIA. So NVIDIA is the NVIDIA is a classic Ethereum test environment. Okay, so you also have the rollup Aztec rollup and the Aztec PXE. Right, this is the PXE. Okay, and then they create three smart contracts wallet accounts. Let's be at least Bob and Charlie. They give them some tokens, I guess. Alright, and then the sequencer is well, the sequencer is like the miner. I think this is the stuff that decides the order of the transactions, and the stuff that creates the blocks. They call it the sequencer. Okay, the current sandbox does not generate or verify proofs, but provides us working end-to-end developer work. Right, so this is not operational, fully operational, in the sense that this normally you would have to generate ZK proof, and you should have verification of the stuff that you submit uh, by the uh, by the Aztec nodes. But at this point, it is not working. So they're more focused on enabling developers write or design smart contracts. And then we have a CLI. Okay, so a CLI is yeah, if you want to issue commands without having to use the Aztec JS, so you don't want to write JavaScript at all, then you can use the command line interface. Okay, so it can be used to deploy, compile, and invoke contracts. But all this stuff is probably done, can also be done through the JavaScript interface. Okay, next commands. Yeah, the CLI is actually written in JS. Okay, Docker. So I think we already have that in our sandbox because we were calling Aztec-CLI. So we don't really need to be concerned. Yeah, Aztec.CLI, we were calling that already. And it has this create account. Okay, when you create an account, you get an address. Makes sense. You get a public key, and I don't know what's the partial address. All right, what's the partial address? Okay, let's see partial address. Public key. All right, this is the same as the first part is the same as Ethereum. The contract code is hashed, and then you get an address based on the hash of the contract. That means that if you change anything in the contract, then you will have a different hash. So all the contracts are immutable, which is this is the rule that every blockchain has. You cannot change the contract. You have to deploy a new one. And then you have hash sold contract code constructor hash. Right? I don't know why you have a partial address, which is a hash, and then oh, so the public key doesn't change, but the partial address changes with the contract code. All right. So the idea here is that as the owner of the account, you have a public private key pair or private public key pair, which then is hashed with the partial address, and then to have the final address. Mhm. Okay. So I think there's probably a reason for that, but the public key corresponds to manage for a state such as zero encrypting node. An account needs to share. Oh, okay. So that gives you the reason why they don't. Because normally you have all this stuff together in the account that creates the stuff would have also it would be also here, but they separate in two steps, and the reason is here so that you can send a partial address to someone, and they can send you the stuff, and they can verify that uh, the the address, the final address, is really the hash of your public key and the partial address. Okay. Mhm. Okay, so that's fair. The privacy master key is used to derive encryption keys. Encryption keys are there. Right, okay. So this stuff here is really for sending encrypted messages uh, from contract to accounts or accounts to contracts. Okay. In a future version, encryption keys will be differentiated between incoming and outgoing. When sending a note to another user, the sender will use the recipient incoming encryption key for encrypting data, and will optionally use their own outgoing key. That's actually for on data, for example. Data. All right. So this is actually very similar to what Zcash does. When you send a message, you are encrypting that. Well, it's the same for every messaging system. When you send a message to somebody, you're using their encryption key to their incoming encryption key to encrypt your message. So, because normally you don't need to read the message, right? So they give you their key, and then they they give you their public key, and you're using their public key to encrypt the message, right? And but that makes your message you cannot decrypt your message anymore, right? It was encrypted based on the key of the recipient. So you optionally have the ability to also provide your own encryption key, so the outgoing one for yourself, the sender, so that if you see that message in the blockchain, or if you receive a copy of that blockchain, you're also able to decrypt it. So the same message is can be decrypted by two people, the recipient with the incoming key and the sender with the outgoing key. So it's well, it's pretty much the same as Zcash. And in Zcash, it's called outgoing key and incoming key. The outgoing key, and it's also optional. I think that all wallets do that. They always encrypt the message with the outgoing key as well. An application in Aztec can access the encryption public key for a given address. So every address has this public key, right? So that allows anyone to save encrypted messages to any contract, to any smart contract. Okay, this part I'm not sure. Alright, and then we have nullifiers. In addition to deriving encryption keys, the privacy master key. So the privacy master key is the guy over there, right? We have up there. Privacy master key. Okay. Unlike signing keys, privacy keys are enshrined at the protocol layer, are required to be Chromekins keys and are tied to the account address. Okay, I'm not sure I understand that, but it's okay. Let's see, nullifier sequence. The privacy master key is used for deriving nullifier sequence. Whenever a private node is consumed, a nullifier deterministically derived from it is emitted. This mechanism prevents double spend since nullifiers are checked by the protocol to be unique. Now, in order to preserve privacy, A third party should not be able to link a node commitment to its nullifier. This link is enforced by the node implementation. Therefore, calculating the nullifier for a node requires a secret from its owner. An application can request a secret. Okay, so what it means here is that when you have private state, um, you can't just go and then change the private state. Let's say that the private state is a counter, and then your contract maintains this counter. If you want to change the value, you can't just go and change the value because it would be trivial for an observer to see that that slot, that value in a particular slot, yeah, has changed from 1 to 2. But I mean, they can't see that it's 1 to 2 because it's probably going to be encrypted. But they can see that the value is changed, so they can trivially figure out that your smart contract is storing some state in that particular index, and that smart contract is also executing something. So that information is already too much for a system that is meant to be private. Therefore, what you do is you consider that everything is immutable, right? So if you change something 1 to 2, first of all, it's not 1, it's going to be like, let's say 42, and then after change, it's going to be 64. With homomorphic encryption, you can do something that still preserve some math properties. But anyways, it's going to be encrypted, uh, but it's also going to be like visible. What you're going to see though is that the 42 is not changing to 64. You're going to see like basically some storage somewhere that has all these values, 42, and suddenly there's another like 64. But you cannot relate the 42 to 64 because in between there's going to be a lot of other values that are completely not related to your own storage. But to make sure that your 64 is actually deleting this 42, you are going to provide this nullifier. And this nullifier uh, forces you to only change the 42 once. Because if you provide another, if you try again to do a modification, you are going to provide the same nullifier. So all I'm trying to say is that every slot that is out there that stores the private state is going to have a nullifier associated to it. And these nullifiers will be the result of some compute node hash for read and nullify. So this function here, the node is actually your private state, and so you're computing a nullifier, so that later if you want to change it, then you have to provide that nullifier. This is really the same idea as a tombstone. In a database system where things cannot be changed, instead of saying that you are deleting or updating a row, you are providing a tombstone, which is kind of like the anti value, and that value allows the system to understand that something has been deleted or updated. Uh, okay, so scope keys are not in here, therefore they are not gonna be. Okay, we'll need to read about that. All right. So we know what this stuff means, right? The public key, private key is something that is really uh, random and associated to us, this new account. Then you derive the public key. This guy is probably is the uh, probably the privacy master key. Then you have the public key. You have the partial address of which is the hash of the. It should be the hash of the smart contract. And here, there's no smart contract. Maybe the smart contract is implied for accounts. Yeah, privacy key. So this private key is a privacy key. And then, okay, you can save that somewhere. And then create account from private key. You can also manually generate a private key. And it's okay. So this is just the alternate version, where you create a key pair, and then you create the account based on the private key. Okay, so that's just a two-step instead of one. Okay. and then you can store the private key into these variables that you don't have to provide it on the command line. Get accounts is all the accounts have been. So it was by default you have three. So now after the create account you have a fourth one. Yeah, so three default accounts is the four, and then deploying a token contract. Okay, so you deploy something. Okay, so okay, that guy here must be some contract that they have already compiled, or some contract that they have already injected in the sandbox. But I don't think this is like, I don't think this is magic. There should be the source code of this token contract artifact somewhere. Maybe they explain that later. So you deploy that guy. Oh, already also this tutorial, right? So you can write this contract, and then once you deploy, you have an address, and then they save the address. Okay, so far so good. Check deploy. When you pass the address, and they say, okay, this is found. So the stuff here though is that if you don't store the contract address, I don't know how to where to get it, and that was the problem we had. I ran it, and then I didn't have JQ, therefore the command executed. But the second part where the we were passing the output, that part didn't work out, and then I was left with a contract deployed, but no knowledge of where it was deployed, and then I couldn't check if this line was not. I mean, I couldn't execute this line because I didn't have the contract address. So I don't see how to solve this problem based on the documentation so far. But okay, we don't mind that. And then we do a send mint public. Um, okay, this mint public must be should be a function that this smart contract defines. I don't think this is magic. This is, I mean, I don't think this is something that is hard coded. So I believe this is a method of this smart contract. So this is the name of smart contract, the address. You have to put a private key and da. Okay, that makes sense. And that create a transaction. So you have to provide your private key because you're minting something, therefore you're creating tokens. And if you're creating tokens, you should be able, I mean, you should have to provide the private key. Transaction mean, huh? So what is 543 though? Oh, 543 is just the amount that you're minting. So we are minting 543 tokens for this address here. So this is public minting. So everybody will know that this address has these tokens, right? And then once it's bind, you have this receipt, transaction hash, block number, all this crap. Okay, that's very special. But I think the interesting part is how to do a private minting. All right, and then if you want to call a balance, you can call this. Okay, no problem. Sandbox reference. Hello. How do we do a private meeting? Okay, this is jumping. I was expecting more information. Okay, go back. Oh, this is really weird. This documentation is weird. Okay, I think they need to update this. This is not complete. Or or they don't want to go into too much details because I mean this is sending a transaction through a CLI. Minting a private token is still also sending a transaction, so it doesn't really matter in this particular section of the documentation whether you're minting private or minting public. They just want to show how you would call a function that mutates the state. And if you want to know how to privately mint, it's more about the content of this contract, which is here. So if we can take a look at this guy, we know how to do private minting. All right. So I think that would be interesting to see later. So I'm going to stop here, and we're going to take a look at this smart contract in the next video.